Hey kids, this time we are going to work with infinite series tests. And what I mean by that is we have asked you to find sums of infinite convergent geometric series, right? We've asked you to do that already, but what if it's not geometric and I want to know if it converges? And remember, we talked about converging being this idea of adding a bunch of terms of a sequence together, but the terms get so small that when you add them and add them and add them, they stay underneath this upper bound. Versus a sum that diverges, where you add a bunch of terms of a sequence and that sum just grows without bound and busts out the house. So the question becomes, what if it's not geometric? How can I test to see if a series is convergent or divergent? And I told you in the last video that what we're really after is convergent series. I want to know if something's divergent, then I'm going to throw it away. If it's convergent, I'm going to keep it. We love convergent series. So what we've done so far is, in the last video, we talked about an infinite series converging, and if they ask me for the infinite sum, that bound, that height of the house, the top of the ceiling, the top of the roof, I only have one formula for an infinite sum, and it comes from a geometric series, right? Where it is the first term over 1 minus that common ratio r. Otherwise, I don't know how to find the sum. So when somebody asks me if the series converges, I look to see if it's arithmetic. How do I tell if it's arithmetic? I look at the terms and I see, is there a common difference? If there's a common difference and it is arithmetic, the series diverges. Call that the arithmetic series test for divergence. Test to see if there's a common difference. If there's a common difference, you know your series diverges. However, if you look at your series and find that it is geometric, in other words, you look at the terms and you divide the term by the previous term that came before it, and you get a common ratio, then you have a geometric series, and the geometric series test for convergence is identify that R, and if that common ratio, absolute value of, is strictly less than 1, then you converge. Otherwise, you fail the geometric series test for convergence when your common ratio is greater than or equal to 1 and your series diverges. Right? So remember, when you think about the right, when you're looking at a series, whether it's in sigma form or whether it is just term by term, these are the things that you know so far about a series converging to a sum. An arithmetic series, the sum will grow without bound because the terms grow without bound. For a geometric, the terms go to 0 when the absolute value of r is less than 1, and the sum they get small enough so that your sum will be contained within the house, but not if r is greater than or equal to 1. So the issue is, what happens if the series isn't arithmetic or geometric? When somebody asks me if the series converges, the first thing I ask, is it arithmetic? And if that answer is no, the next thing I ask is that series geometric? If that answer is no, the next thing I look at is the sequence of the terms. And I ask myself, the next question I ask myself is, do the terms go to 0? So look at these terms, not the sum, the terms. Here's the rule for the terms. Look at the limit of the sequence. Does the limit of the terms go to 0? N to the first, 2n to the first. This limit is equal to 1/2, which does not equal to 0. So if the limit of the terms doesn't go to 0, you do not have a chance for the sum to converge. Remember, for the sum to converge, the terms have to be getting smaller and smaller and smaller and going to 0, but they also have to get small enough. Just going to 0 isn't good enough, but if your terms don't go to 0, you don't have a shot. That is a test for divergence. Again, you look at if your series is not arithmetic and it is not geometric, you ask yourself, if the terms of the series do not approach 0, then the series is divergent. That is called the nth term test for divergence. So you have the arithmetic test for divergence, you have the geometric test for convergence, where if you fail it, the series diverges. Then you look at if neither one of these tests apply, you go to the nth term test and you look at the terms. Do the terms go to a number that's not 0 or go to infinity? Then the series diverges and you're done. Be very careful with this test. Don't use it backwards. In other words, the converse, right? The converse, this is P arrow Q. You cannot say that if a series diverges, the terms don't go to 0. Right? If the series the terms do not go to 0, because that's not true. It's also not true that if the terms do not approach 0, in other words, they do approach 0, don't assume that the series doesn't diverge or therefore converges. None of those are true. This is only the nth term test for divergence. If the terms of the series do go to 0, you might converge, but you might also diverge, and you have to use another test to figure it out. For instance, look at these two. So the first thing you ask yourself, is it arithmetic? No. Is it geometric? No. That's 1 and that's 2. 3, look at the terms. The limit of the terms is 1, right? Even powered is 1, which does not equal 0, therefore diverge by the nth term test. But look at this example. Is it arithmetic? Right? Write out the terms. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Is it arithmetic? No. No common difference. Is it geometric? No. There's no common ratio. 3. Does the limit of the terms go to 0? Yes. The limit of the terms goes to 0, which is inconclusive. This series might converge or diverge. I need another test. Let me give you another test. The P-series test for convergence. If you have an infinite series of this form where 1 is in the numerator over n to a power, if that power is greater than 1, the infinite series will converge to a sum. Notice no one asks you what the sum is. You can't find the sum of an infinite P-series until you get to calculus, because it's not a formula, it's a process. And it's a process that takes calculus. If the power is equal to 1 or is less than 1, the P-series will diverge. You fail the convert P-series test for convergence. So let's do some examples. Look at this one. When P is equal to 1, here's what the sum looks like. And here's my expanding. This diverges because it's a p-series where p is equal to 1. So notice the terms, the first thing I did was say, is this geometric? No. Is it arithmetic? No. Is it geometric? No. Do the terms go to 0? Yes. Need another test. P-series test. That's my fourth one. There's very few famous divergent series. This is one, harmonic series, and yes, it does have to do with music. Look it up. Here's what this series looks like. I wrote out some terms. It's not arithmetic. It is not geometric. The terms do go to 0. Therefore, I checked to see if it was a p-series. It is a p-series. It converges because I recognize the p-series form. P is equal to 2, which is greater than 1. Not so bad. P-series test for convergence. This series failed the p-series test for convergence and therefore diverges. How about this one? P-series diverges because it's a p-series where p is equal to 1/2, which is less than 1. All right, so far, arithmetic, geometric, nth term, p-series. Oh, I forgot. What's pretty cool is that not only did Euler use calculus, which I don't think Newton had come about yet to do. Anyway, he showed that this series does have a sum. He did not use the a over 1 minus r formula because that's for a geometric series, but Euler showed that the not only does 1 over n squared converge, it converges to pi squared over 6. It's kind of cool, isn't it? All right, so does the series converge? Notice no one asked you for a sum. So you're going to look at, again, first, is it arithmetic? Second, is it geometric? Third, does it diverge by the nth term? 4, is it a p-series? And hopefully you can see that each one of these is a p-series. And what would you say? Right? Converge, p-series, p is greater than 1. Converge, p-series, p is greater than, p equals 3 greater than 1, p equals 4, which is greater than 1. Diverge, p is equal to 1/5, which is less than 1. Converge, p is equal to 5/2, which is greater than 1. Okay, NBD. What about these? Look at those. Each one of these is purposefully very close to the p-series that you just found. So here is a situation where I really, really wish this was a p-series. It's super close. It's very similar to a famous function, right? My unknown series is similar to this famous p-series that I already know converges. So this is a test to use when your series looks really close to a famous p-series or geometric series. So this looks very close to a p-series where p is equal to 3. You know that the similar famous series converges all you have to show for this appropriate test, the terms of your unknown compared to the terms of the similar famous series. So let me draw a little picture here. I'm going to draw a graph of the terms, not the sum, the terms. 1 over n cubed is going to be green, right? The terms go to 0, and because it's a p-series, I know that not only do the terms go to 0, but the sum converges. Talk to me about the terms of the unknown. Talk about their position. So think about this. 1 over 1 cubed, 1 over 8, right, which is 2 cubed, 1 over 27, which is 3 cubed. Isn't it true that the terms of the green series are bigger than the terms of the unknown series? 1 over, this would be 2. 1 cubed plus 1, 1/2. 1 over, not 8, but 9. Isn't 1/9 smaller than 1/8? Since you know the green p-series converges because your unknown similar behaving function lies under it, the terms, each term lies under it, therefore the unknown, so I'm going to put a big 1 over, right, the similar is bigger than the unknown, and the similar converges. Therefore, the unknown must converge to, and we call that the direct comparison test. Because what I did was compare term by term the values. And since the sum of these terms converged, because I had a p-series where p was greater than 1, the similar one that always lied below it must converge as well. That's the direct comparison test. Let's do another example. Look at this one. I have, why would I compare it to 1 over n to the 4th? Do you see? If you're going to infinity, this plus 3 doesn't really matter, and n to the 1st over n to the 5th reduces to 1 over the 4th, right? So you can kind of sort of think of this as 1 over n to the 4th plus 3, right? I know that's illegal algebra, but when I'm talking about going to infinity, that plus 3 doesn't matter. I'm going to do a term-by-term comparison. You know that 1 over n to the 4th converges because it's a p-series, so it's the exact same scenario that I have up here. The terms of 1 over n to the 4th are all bigger than the terms of n over n to the 5th plus 3, which I kind of can sort of think of 1 over n to the 4th plus 3. Since I am directly comparing in terms and the convergent terms all lie on top of the unknown terms, the unknown converges as well by the DCT. Now I have to draw another picture for this next one. One over n to the 1/5 is a divergent series. The terms go to 0, but they don't go to 0. It doesn't go to 0 fast enough for the sum to converge. However, Look at the similar unknown function. This similar unknown function subtracts 1 in the numerator. In this case, oh, I wanted to make that blue. The unknown series, the term-by-term comparison, those terms are all bigger than the known. Unknown, known. But what does the known do? The known diverges. If the known diverges, it catches the terms that are all bigger than it. Therefore, my known diverged. My unknown terms, when I did a term-by-term comparison, was all above the divergent ones. Therefore, the unknown diverges as well. By the direct comparison test. Notice that the super important piece of the direct comparison test was converge, the similar has to be bigger than the unknown. Diverge, the similar has to be smaller than the unknown for you to be able to make that conclusion. So let's look at this last one. The known is a p-series. The terms go to 0, and they go to 0 fast enough so that the sum converges because p is greater than 1. What's true about this very, very similar series? Just the numerator that's different. But can you see that multiplying by 5, when you do a term-by-term comparison, the terms are going to be bigger, right? But what do you know about the known? It converges. The sum converges. So the direct comparison test cannot be used because the position is wrong, right? The known convergence series is all smaller, right? Smaller than. But for convergent, you need the similar to be bigger. Convergent, smaller, DC comparison test, direct comparison test can't be used. I need a different test. That's tomorrow. I'll give you a hint though. If you think about osmosis thing, this 5 out, you have 5 times a convergent series. If this series has a roof of 4, multiplying that roof by 5 is just going to give me a roof of 20, but I still have a roof. So it is going to converge, but I can't say that it converges by the direct comparison test because the position was wrong. A series of positive terms is convergent if each of the terms of the series is less than the known one. Right? Your unknown is convergent if the unknown terms are under the known or famous series. The unknown series is divergent if, when you do a term by term comparison, the unknown is above the known. I should say not some other, I should say known positive convergent series. So here are my steps to do the DCT converge, right? Remember, first, when somebody asks me, is it arithmetic? No. Is it geometric? No. Look at the term, limit of the terms. No. Is it a p-series? No. Can I compare it? Is it similar? Is the series they're asking me about similar to a geometric or p-series? Choose it. Tell me which one right? This is your known, famous, similar, known, famous, behaving series. Tell me about that series. Does it converge or diverge, and why? So you're going to say, oh, it's geo with a common ratio of this, therefore it does that, or it's a p-series with a p of this, therefore it does that or this. Then you must tell me about the position. If your known function converges, then what you don't know has to be under it, and you just have to make a quality statement, right? Diverge, unknown must lie above it. Think about those graphs and then make your conclusion, right? If your known converges and you have the right position, then your unknown converges by the DCT. If your known diverges and your unknown is above it, then your unknown diverges by the DCT. I know that sounds kind of crazy, but there's not you're writing stuff here, but you're not doing an awful lot of math, right? Choosing this, you're going to just, if anything, just forget to state that. Make sure you know the correct position and then also state your conclusion. And we'll practice this in our next live session.